All right. Good morning, good afternoon, everyone, wherever we may be. Today is my great pleasure to be introducing to you some new technology that we've been working on for quite some time, which is our support for NVIDIA GPU through the CUDA technology. My name is Quentin Ochem. I am a Chief Product Officer at Ada and in particular, I'm responsible for product management. And that's the reason why I'm set today to dive with you in this new product that we are about to make available to our customers. So to start with, one of the things that, I'm assuming that a lot of the people in this webinar are familiar with CUDA, but just to recap. And by the way, before I move too much into it, if you guys have any questions, you will find in the WebEx interface a chat view and a Q&A view. So you should feel free to put your questions in the chat or in the Q&A, and I would be happy to answer to these questions at the end of the webinar. Now let's get back to CUDA. CUDA is a technology that is provided by NVIDIA and that essentially allows developer to write user code running on the GPU itself. Now that's quite interesting because as you may know, GPU, which stands for graphical processing unit, used to be used back in the days to sustain gaming, essentially. I mean, they were very good at rendering real-time 3D graphics, but it turns out that the kind of things that they can do goes much further than that. And today, any kind of code that leads itself well to vectorization can be run on a GPU. The application ends up being essentially a distributed application between two parts. One part is the host. So that's a regular code that will run on a PC, for example, or perhaps an ARM. There are a couple of special constructs in there, but it's mostly what you would expect from a normal application. And then you have another part, which is a device, which is doing some of the computation on a separate computer, essentially. Now, what's interesting with CUDA is that it is very well aligned with fine-tuning for NVIDIA-specific hardware. You can really get the most of the hardware. You will have to do things such as refining, the scheduling, memory management, and so on and so forth. But with that, you can really optimize quite a lot the overall performances of the application. So just to recap, what you're looking here on the screen is a typical CUDA application. So you have two computers, essentially, that are communicating with one another. The main computer is essentially the CPU computer. We have a few powerful cores. They can do very complex stuff, very complex control flow, if you will, but you don't have many of them. On the GPU, on the other end, you have a lot of cores. In the order of thousands, of course, but they are much smaller, and typically they are less powerful. They can run instruction together, but they're not so good at running different instructions. So, for example, if you have a sequence of statements with no branch, then you're going to be able to have all your cores being able to run a given computation. But the minute you have branches, some of the core are going to have to wait for one side of the execution to be done and so on and so forth. So you want to be very mindful of which computation is run on the CPU and which computation is run on the GPU. And you'll go back and forth to this process called offloading, where you will at some point copy some of the memory on one side, launch a computation maybe in parallel, then come back and so on and so forth. So that is CUDA. Now, GNAT for CUDA is an extension of the NVIDIA CUDA technology. That extension is provided by Ada Core, and it essentially enables to develop Ada and Spark code running directly on the GPU. Or said in a different way, it allows you to develop a cohesive, distributed Ada and Spark application which will run partially on the CPU and partially on the GPU. So why might you want to do that? Well, there are two main reasons why this is potentially interesting. The first one is if you already have Ada code around and you also happen to have access to NVIDIA hardware. Using this kind of technology is a great way to increase the sheer performances if you do have algorithms that lend themselves well to vectorization. A typical example is signal processing. You could offload a lot of the signal processing computation to the GPU and get improvements in the order of maybe 100 times faster of that specific computation. Now, what's nice is the fact that you have this consistent language across the board. You have the Ada language on both sides, so you can really share things such as data types. You can also share processing to some extent. You can run the same code on the GPU and the CPU if needed, and so on and so forth. The second use case is for people that are developing new code. That would be new Ada or new Spark code. And then really, you can do something like develop high integrity code or even formally proven code if you're using Spark on the GPU itself. So all this goodness, all of this value of the Ada and Spark languages, you can harvest, if you will, on the GPU itself. So that's for the overall positioning of the technology. Now, let's have a look at concretely what does that look like. And I'm going to start with describing a small piece of CUDA C code. So this is something that you could write with the NVIDIA toolset. Essentially, to write a CUDA code, you need to identify an entry point. We call that a kernel, which is a function that is going to be called in parallel many, many times on the GPU device. You can identify such function by this global annotation here that you see at the top left corner of my screen. So that's enough to say to the CUDA toolchain, hey, this is a kernel, this is an entry point to the parallel computation. And within that kernel, you're free to do whatever computation you might want to do. In this case, I'm doing a matrix addition. So I want to compute the result of A plus B and store that into C. Every single call of that function, which will be called on different threads, will compute the value on one specific item of the matrix. To retrieve that, which item I want actually to work on, I can do some arithmetic based on the index of that call in the scheduling. So for example, each call is here identified by a thread ID and a block ID. It doesn't really matter what that means. If you're not familiar with it, suffice to say that this gives me a unique identifier for the given call to that vector add function on the GPU. So I'm using that to compute an index, and then I'm doing the addition based on that index. Our objective is for the Ada code to look as close as possible to the C code so that if you have CUDA expertise, you won't have too much to learn. And notably, we are reusing the same kind of annotation to identify a kernel. So you see here, I've got this vector add procedure, which is marked CUDA global, which means this is an entry point. This is a CUDA kernel. Now, interestingly, already, this is Ada. So in C, I had to pass the number of elements of the array. But in Ada, I'm dealing with unconstrained array. That information is carried by the array type itself. So I don't need to pass that as an extra parameter. If you look at the body of the procedure, you'll see that the way I retrieve an index is quite similar. And then the way that I'm computing the values and verifying that I am within boundaries is also quite similar. Now, this is the device code. That's the code that is going to run on the GPU. Let's look at how to run this code from the CPU, how to load this code and call this code from the host, from the CPU. Again, starting with CUDA. Here, I'm going to allocate 3 arrays on the device. So you see that the first array here are regular malloc, so that's a CPU memory allocation. Now, typically, GPU have a separate memory. It's not true for all architectures, but in the specific example, it's the case. So I have a different address space for the GPU memory, and I'm allocating this to the CUDA malloc. Interestingly, from a C perspective, there's nothing that distinguishes host pointer from a device pointer. So you can see that there is some room for mistakes here. We'll see with Ada that there are ways to improve the situation. I'm then doing here explicit memory copy from the host memory to the device memory, preparing the data for the computation. And a couple of lines later, I'm going to make the call. So this is saying essentially, please call vector add on this number blocks, this many blocks, and this many threads using those parameters. This will essentially generate hundreds of thousands of calls on the GPU to that what function vector add. Once the computation is done, I'm going to be able to copy the memory back from the device to the host and then hold the result of my computation in the host memory space. Now, if you look at the Ada version of that, we have a little something in Ada called strong typing. So the first thing that I'm going to do here is to identify 2 pointer types. One that is going to be specific for host memory, one that is going to be specific for device memory. So you see here, those 2 types declared. On the device pointer, I'm going to specify the fact that this device actually points to foreign memory, which is modeled by this CUDA storage model object here. That's a new capability, that this designated storage model that we developed specifically to support in particular CUDA. But now the compiler knows that objects that are pointed by the first pointer point to different memory model than the second pointer. So when I'm doing allocation here, I don't need to explicitly call the CUDA API. The compiler knows how to call the right allocation functions, because it knows the type of the access type. Similarly, here, when I'm doing copy, I don't need to manually call the CUDA APIs anymore. The compiler knows that I'm doing a copy between host memory and device memory, and it's going to instrument that copy using the CUDA API underneath. But from a user perspective, I can just do a regular assignment. Now you can see the next call, which is the actual call to the GPU. And sure enough, I'm passing here the 3 parameters. I'm providing a number of threads and a number of blocks, just as before. And then finally, I'm going to run that copy in the other direction. So here you can already see that thanks to the fact that I'm using Ada, there is some level of type safety that I can inject in the processing in order to maybe avoid certain mistakes that would be more difficult to avoid if I were doing C. Now, in terms of the build process, there are 2 applications to build. So we have 2 tool chains, actually. You have one tool chain, which is the device tool chain, which is going to compile the code in a library that is going to be loaded onto the device. And then you will have the host tool chain, which will do the usual stuff, compile the host application, and take that library, link against it to be able to load that device library to the GPU at start time. Now, one note at this stage, when I say host, I don't really need native. In other words, I don't need necessarily x86. NVIDIA has maybe 2 category of technology, I would say. One is dedicated GPU. So that's typically the thing that you have for your gaming boards. That's what I have on my laptop here. That's what you might want to use for high performance computing, where so you have x86 system together with a board, sideboard that be essentially the GPU. But NVIDIA also sell a system on chip called Tegra, which embeds together both a GPU and ARM core. And this is typically something that you would run with ARM Linux. This is also supported by our technology, and that's a use case that is much more common in the embedded world. I want to show a demo of what that looks like, but before I do, just know that there's now a beta available of the technology. If you want to try it out, we will need to discuss with you to make sure that your use case is supported by the technology in its current state. But if you want to try it out, please contact us on info@adacore.com, and we'd be very happy to start a discussion. Now let's look at this thing live. I want to show a piece of example that is a bit more interesting than the just a vector addition. I'm going to show to you something called the matching cube, algorithm, which is an algorithm that converts a density function, which essentially says there's something here and nothing there, into a 3D shape, a triangle mesh. This code, by the way, is available as part of the example that we ship with the technology. So you can see here that I've got two kernels, two entry points, which are marked CUDA global. This one is used to clear or reinitialize some data, if you will. It doesn't even have a parameter. And this one is the main code that I'm going to run on the GPU. And already here you can see that this is not trivial. It really feels like I'm writing a proper Ada specification. I have three array access. I have structures, point real, point int. I have some access to integer. I have default parameters. And actually, if you look at this objects, those arrays, they're actually not trivial at all. Let's see if I can show you some of the definitions. So this ball array type here, I believe, is declared in that other package. So it's an unconstrained array that contains balls, which itself is a record. So I'm really manipulating complex data structure here across the boundaries of the CPU and the GPU. Okay. Now, if I enter to the actual code, you'll see that the first thing that I'm doing in this entry point is actually to call a second function, which is a function that takes into parameter the actual cube that I want to compute. The reason why I'm doing that is that this one is really the entry point to the GPU, but I want to be able to call that computation both from the CPU and the GPU for debugging purposes, for example. So this is a very typical architecture where you are just using the entry points to call a piece of code that is actually compilable to both the GPU and the CPU. Now, I don't want to go into the details of the algorithm. If you want to check that out on the web, the matching cube is a very well documented algorithm. But one of these characteristics is that every cube of the space that you're going to compute can be computed independently. So conceptually, this is something that should work very well on a GPU. However, the computation itself is far from being trivial. If I look at the code, you will see that I have local subprogram with control flow all over the place. A couple of conditions here, complex computations. You can see that I have nested blocks. I even have nested subprograms here. This is a nested one. I have atomic function that I'm importing from intrinsics. I can see like other global variables that are going to be used and stored. What else? For loops all over the place, and so on and so forth. What I'm trying to demonstrate here is that this code is just a regular piece of Ada code. It's far from trivial. And when I wrote it, I didn't necessarily write it too much with GPU in mind. I had the big architecture to make sure that it could work. But after that, in terms of the feature that I'm been using, I am really using regular Ada code. Okay. Now, an interesting aspect that I want to look at in terms of performances is that the more branches you have in your code, the less typically performance gain you're going to get, because each time you have a branch, you have effect in the GPU that may lose some of the cycle. But we'll see how good this code behaves. On the host side, you will see that, first of all, here I have those special array types that I talked about earlier. So with the designated storage model to be able to do the instrumented copies. And now on the host side, what I'm going to do is allocate the memory on which I'm going to work again. It really looks like I'm doing regular Ada, although here I'm because I'm using those specific types, I'm actually instrumenting the allocation here using the CUDA API. Actually, it's more than that. Because I'm doing Ada, I can just allocate. I also need to initialize boundaries, copy the boundaries of those arrays to the device. All of that is done under the hood. Then if I want to do the CUDA computation, I'm going to do some further initialization, some further copies. You can see here that I'm doing the first call to one of the kernel, which is a kernel that is initializing my global state. And then here, I'm calling that complex CUDA marching cube function. And in this very example, we even do things proper. At the end, we are deallocating the memory that was allocated to the device, which is making sure that everything is clean in the end. Okay. Now let's look at the performances of this piece of code. Let's already start with CPU. So this is a single thread CPU computation just for reference. And you can see here that each frames takes about 1 second essentially. It's a very slow computation. Now, of course, this is not very fair to compare at that level because I've got a multi-core machine. So if I do this second call, I am now calling this same computation, spreading that on as many core as I can. And you can see that I can, bring the computation of a single frame to 200 milliseconds, which is already quite a significant improvement. This is essentially as far as I can push my CPU to compute and run that application. And now if I'm trying that using CUDA, you can see the number popping up already. And unfortunately, because of the fact that we are online, you don't see how fluid this is, but you see the number, right? I am now computing one frame in 7 to 8 milliseconds, reaching almost 150 frames per second. So this will tell me two things. It's first and foremost a testament of the power of the NVIDIA technology. I mean, I have a fairly recent laptop with a fairly recent GPU on it, but that's a laptop nonetheless. That's not a high performance computing machine. That's not a gaming machine by any means. And this also shows that we could exploit and harvest that power in an application that is fully written in Ada. Okay, so I go to the end. We're not done with the demo parts. We have a few minutes for questions. I'm going to answer them as they came in the chat view. So the first question is: does TensorFlow or PyTorch already make use of the Spark language? The answer is no. We don't even have Spark APIs to those languages yet, but this is something that we could look at. But definitely, they are not implemented in Spark. Second question, is the sample code available on GitHub? The answer is yes. Unfortunately, the toolchain itself is quite difficult to build. So if you just get GitHub, you can look at the code. If you go to our Ada core GitHub, it's under the CUDA repository. However, you will not be able to compile it without having access to the technology that we provide as part of the beta. Does GNAT also support AMD ROC, or is there plan to support it? So right now, we do not support any other GPU technology. We selected specifically NVIDIA hardware because when we looked at our markets, in particular, people that are doing embedded application, we saw a lot of NVIDIA hardware out there. So we felt like this was the first target to consider. We have in the books some plans to also port to OpenCL to do something similar to support a much wider range of GPUs, but this is something that is down the line in a few years. Right now, we're really concentrating on getting that CUDA product out there. Is it possible to synchronize kernel with CUDA Ada? The answer is yes. You essentially have access to the same kind of API, or will have access to the same kind of API as you have with regular CUDA. At this stage, there are a lot of gaps in this API, but we're looking at completing it. Next question, SparkProof is highly parallelizable. Will you investigate the use of GPU to speed up Spark analysis? At this stage, no, because the kind of parallelization that you get with Spark doesn't seem to link itself very well with what GPU can do. I mean, essentially, in the marching cube example, even if I have a lot of conditions all over the place, it turns out that most of the computation goes the same way, so follows the same route, which explain in part the performance increase. We do not believe that this will be the case for the Spark analysis at this stage. So we have no plans to look at harnessing GPU power for that specific aspect of formal proof. Next question, what is the performance between CUDA and Ada CUDA? So that's a general question, by the way, that goes beyond CUDA, sorry. Generally speaking, there is no reason to believe that there is any significant difference between the two environments. We haven't seen anything. We haven't had a lot of time to develop benchmark, but we're essentially using the same technology. The backend of CUDA and Ada is the same LLVM backend that NVIDIA provides, and same for the hosts. We're using the GCC that everybody is using. So in terms of performances, if you're doing the same kind of thing, you know, the usual question, you know, remove Ada checks and so on and so forth, there's no reason to have significant differences between the Ada and the C versions. That presentation is recorded, I hope so, to the next question that was asking if it was recorded. So we will make the recording available. Is Ada CUDA compatible with all versions of the CUDA driver? So we have experimented with the newer ones. For the old ones, we could, I can't remember the streaming processor version that we run that on. I think it was in the 60 series. So it won't support very old hardware, essentially, most likely. I mean, even the CUDA driver are not updated for this old environment. But for anything reasonably, let's say, that has been released over the past 10 years, we should be able to generate code for it. Will Ada CUDA be open source? I think that there are two questions to that. Will it be open source? And will we be making builds available to the community? At Ada Core, everything that we do comes with open source licenses. So when we provide technology to our customers, it is provided with open source licenses. However, we don't provide all the software that we built to the community. There are ways to look at what we have and building yourself. It's difficult, in particular in this context, because a lot of this technology is very recent. I would personally love to make that technology available to the community. I think it's a great use case for Ada. It's a great use case for Spark, and that's something that would be very cool to allow people to use. We don't have plans yet, and I think that we would definitely want to have reached some level of maturity before letting that technology go out there in the wild. Is NVProof or tools are compatible with CUDA Ada? The answer is yes. I actually had an NVProof demo for today, but turns out that my version of NVProof does not support my version of the GPU, so I could not demonstrate that. I have another computer at home, which is older in terms of technology, where I could use NVProof as a matter of fact, to optimize that very code that you saw today. The first version was not as fast, and using NVProof, we could actually schedule correctly the kernel calls and optimize performances. Last question, is it possible to share data between kernel and CUDA C? So in theory, yes. There is no reason why the usual interfacing technologies between Ada and C wouldn't work for CUDA. However, this is not something that we have investigated yet. So if you were to do that today, there would be probably significant amount of exploration and manual work. That is definitely like streamlining this process of interfacing between CUDA C and CUDA Ada is definitely part of the roadmap for us. Are there some limitations between normal Ada and CUDA Ada? Yes. In particular, with regards to the runtime that you are available on the CUDA side, so on the GPU side. As of today, we support something that is akin to a bare metal runtime. So you have access to essentially the entire language, but in terms of the library, you are limited. One notable thing that is missing is anything that pertains to real time. So you don't have access to tasks, you don't have access to protected object. This might be something that we look at in the future, but it's not completely trivial to map Ada tasking concepts to the GPU. It's also not clear how useful that is. Another thing that we haven't fully investigated yet is exception support. So right now you have so-called last chance handler exception. So if there's a problem with the kernel, it will just stop the given thread. There is more work to do to improve situation there as well. So if you're familiar with our bare metal technology, in particular what we used to call the light runtime, this is in line with what you'll have, but conceptually, there's no reason not to be able to extend for attending to that call. Again, if you have any question, if you want to try that out, please reach out to us on info.adacore.com. And yeah, I hope that we'll get in touch. Thank you.